Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Let's get started. So welcome. So we're here to celebrate Rick's 60th birthday with a FestSchrift. And you may well ask, what is a FestSchrift? So strictly speaking, a FestSchrift, this is something I know from Wikipedia. I'll have to tell you I'm relying, I'm relying on Wikipedia here. So my understanding from Wikipedia is that a FestSchrift is a book honoring a respected academic. And so in addition to the colloquium that we have today, we're also going to be producing a volume that will collect written contributions. In some cases, that'll really be the same content, a written version of the content you're hearing today. A few people are actually going to be contributing something pretty different for the book, and their reflections today will be more personal. So there will be a book coming. The book will not be available for a few months. It takes a little bit of time to produce the book. So this FestSchrift idea really dates back to last summer. I forget, maybe it was July or August or something, probably like July, when a group of Rick's friends and colleagues realized, gosh, Rick is going to be turning 60, and this was turning 60 in September last year. And, we really should do something special to celebrate that. And I think it was really Peter, actually, who suggested the idea of a FestSchrift. I hadn't even heard of them. But of course, we realized that organizing a FestSchrift, everyone sort of immediately thought, that's a great idea, we should do a FestSchrift. But organizing it was going to take quite a while. We just didn't have the time to get it all organized for September. So, but this time frame of March, I think is working out pretty well for us. And my understanding is that this is often the case with academics. Things happen a little bit late. And so we're really just, following in the grand tradition of having our FestSchrift, a few months after the actual birthday. So one thing I want to emphasize, maybe a bit of a caveat, is that this FestSchrift is not meant to anticipate Rick's retirement. We're celebrating his career and his accomplishments to date, but we're also looking forward to a lot more great things to come. I think I remember Rick saying once something about having to pry his cold, dead hands off the keyboard. So I take that to mean we're in no imminent danger of losing Rick. So we're celebrating Rick's 60th birthday today and not his retirement. The reason I'm emphasizing this so much is actually I've gotten some emails, as I sent out the announcement. I did get emails back from people, hey, does this mean that Rick is retiring? And I wanted to squash all of those rumors right up front. So a couple of logistical things before we dive into the first talk. So one thing I would ask the speakers to do, I hope you're willing, is to sign a speaker release form that we have out front where you got your badges. And the reason for that is in the last week I've gotten emails from some folks who are not able to travel to be here in person. They would really like to be able to watch the recording that we're making of the FestSchrift. And so if you can sign that release, that would be really helpful. If you don't get around to doing that, we're going to have to cut your talk out of the recording that we make available to them, and that would be unfortunate. So we are recording this for later viewing, and we're also streaming it live. So there's people back in Building 99, Microsoft Research, who are going to be able to watch from there. But I'm glad to see the turnout that we have here today. So with that, we don't have a lot of time. We're going to have to be pretty timely with our transition. So I'd like to ask Raj to come up and start. You can take a look at the agenda, and the organization is pretty obvious. The morning is focused on people who knew Rick from CMU, and then the afternoon is more focused on people who knew Rick here at Microsoft, or people who are involved in getting Microsoft research started. And then we finish up with a session that sort of talks about Rick's more eclectic interests. But Raj, why don't you start? Do you have your mic on already?
I think so.
Good.
Am I good? Good to go?
I think you're good to go.
Okay. Good morning. So, FestSchrift, according to some people in Germany that I heard from, long ago, 40, 50 years ago, is a festival of writing. Whenever somebody gets to be about 60, you're supposed to, all your colleagues are supposed to get together, everybody writes a paper and presents it, and it becomes a book. So it is a book, but it's actually a festival of writing. So anyway, so this morning we are here to celebrate a remarkable scientific career spanning an exciting period in the history of computer science and computing. Rick came to CMU in 1979, 32 years ago, and I thought there's a good chance he might continue with his thesis research in vision and AI, but as luck would have it, we just then got a big grant for distributed sensor networks. I said, Rick, we need a distributed operating system for this. He said, I've been thinking about it. I'm going to do this. Okay. That's how Mark emerged out of all of that. And we had a SPICE group at that time, and he was a natural fit to kind of lead some of the projects there. And so it turned out after 32 years, he has had major impact in many dimensions on the field, and today I think we are here to celebrate his contributions. The reason I chose this topic is I thought he needs one other big swan song after all the things he has done, and this will keep him busy for another 32 years, okay, if he were to choose to get it started at MSR. John McCarthy once said that to get to human-level artificial intelligence, we'll need 1.7 Einsteins and 2 Maxwells and 5 Faradays and 0.3 Manhattan Project. Okay. I'm not sure which of the 3 Rick will be called, whether he's be Einstein of the AI groups or Maxwell or Faraday. I think any one of them, those appellations, would be wonderful if that could be accomplished. So what is human-level AI? I guess forward. So basically today I want to kind of quickly talk to you about various attempts at defining thinking machines and why the time now might be opportune to proceed with this project, and finally what roadmap or agenda we can create to get there. So the first one, we are not talking about creating machines that have mind and consciousness. That's not the purpose here. Nor are we talking about creating useful systems that act intelligently. We are talking about building systems that exhibit the same level of intelligence and competence that most people on the planet have. The definition here is most. When you think of more than 1 billion people are illiterate, you can't say a computer must be able to prove theorems or various other things. That comes afterwards. First, let us kind of see if we can build a basic level human intelligence that everybody on the planet would have, and not just educated people. So Turing onwards have made a number of proposals. The Turing Proposal, I don't know how many of you have read the paper by Turing where he proposes the imitation game, but that most people stop there. But actually, if you read the second half of his paper, he says maybe the way to do this is to create a child machine and educate it. Okay, and he goes into substantial detail. One of the things that shows the context of the time is he says maybe our child machine doesn't have to have eyes or limbs, Okay, and I don't think we'll need to put that restriction today. The most comprehensive effort at creating an architecture and a system for general intelligence was by Newell, the SOAR project. And what he was looking for, that has been his passion throughout his life, is to create a unified theory. Just like unified theory of physics, he was trying to create a unified theory of artificial intelligence, and also general intelligence, because he was also trying to build models of human intelligence. And there were a number of principles and procedure things that he has, they have, pronounced over the period, both Simon and Newell. I listed 2 or 3 of them here. I won't read them. But the problem turns out to be this architecture mainly is intended to be problem-solving architecture for cognitive tasks. And when I remember challenging Alan and saying, Alan, this won't do speech and vision. How can you have production systems doing speech and vision? He said, we will come to that in the second version or something. I don't know what exactly he had in mind. But my own view is, I'm not sure there is such a thing as a unified theory. The next one, there was a paper by McCarthy called The Well-Designed Child, and where he says, let us not worry about what the human child might have. If we are going to have a well-designed child machine, let us give it everything we can give it, and then see how quickly it can learn or do whatever it needs to do. And I'll come back to this in a while. And Kurzweil, I don't know if any of you have read his book on singularity, and basically he says, we are almost there. In another 30 years, we'll have superhuman AI. And his proposal was to reverse engineer the human brain using nanotechnologies and make it run 1,000 times faster. And there's a fundamental doubt I have whether just by re-engineering the bits, whether this system will exhibit intelligence. He seems to think so. It's like, to me, it's like taking a bunch of chips that go to making a PC and throw it on the table and say, compute. It doesn't. It doesn't. You have to connect it in a particular way, and everything has to be synchronized. And so there are a whole bunch of issues on architecture that may or may not work. Nells Nelson, in a paper and book, kind of proposes saying, let's build a child machine, but let's kind of educate it. But my requirement is it must be able to do all the tasks that human beings do for jobs. I think that's too much at this point. And Minsky proposal comes closest to what I think is the right thing in the long run. It is not one unified theory. It's, both in his Society of Minds book and his Emotion Machines, he kind of says there may be many methods of representing knowledge. There may be many ways to make inference. There may be many ways to learn, whether it's statistical learning or, other kinds of, case-based learning or whatever, analogical learning. And let's use all of them. We may have to use all of them because human beings may be using the same thing. And so he kind of goes on to give his own proposal of how that might be done. The main problem I find with all these proposals here is they have a blind spot. They think this thinking machine should have capabilities similar to their own. Turing thinks it will be as good as men in all purely intellectual fields. McCarthy thinks a well-designed child should handle non-monotonic reasoning and introspection. Newell and Simon think they should be able to prove theorems and play chess. Okay, so I think all of them are reasonable objectives ultimately, but we don't have to impose all of them right at the beginning. I would settle for a 4-year-old child, equivalent of a 4-year-old child. That's what I'm going to propose later on. And so here we are. So the question is, why now? And I propose we have had a number of very important advances in the last 10 years in AI, which give me a lot of hope at this point that we can, with a sustained effort, we may be able to be on the brink of getting there. So those of you know, it started with Deep Blue beating Kasparov, And then we had driverless vehicles, the Stanley winning the off-road navigation of 132 miles without a driver, and the CMU system, BOSS, winning the urban challenge. And these things don't happen overnight. These are results of like 25 years of DARPA funding. In fact, when Rick was still at CMU, we would have seen these Terragator vehicles. They would take one step and think for 20 minutes and take another step, And so these things take time, but ultimately they do happen. And so now when we look at what happened in information retrieval and search, Google, Bing, Yahoo, and so on, again, if you look at the historical precedents, Google came out of the NSF funding on the digital libraries at Stanford, and the first search engine, Lycos, was built at Stanford at CMU by Fuzzy Malden. That was the first full text indexing search engine. And machine translation is a very dramatic story. 10 years ago, if you had told me you can produce respectable translation by any pair of 60 languages, I would not have believed it. Today, Google Translate does that, and it's very impressive. It's all purely statistical, unfortunately, and there are now people trying to do hybrid systems. Hopefully, we'll get to the next stage in this. So then the most recent two that happened in the last year is the Watson question answering system. Amazing result. And I would not have believed it if I hadn't seen it. There are all kinds of things they have to do, to answer a question in 3 seconds. And they have to be confident, they have to have the clue selection analysis, the betting strategy, all kinds of things had to go into that. It's not just a question of retrieving a bunch of things like a search engine would do. To me, that is the next challenge. I call it the village Google. There are 1 billion people that are illiterate. They can't use Google or Bing or any Yahoo. However, they can ask a question, and they want answers to that question in speech, in any language. And I think it can be done. We have beginnings of it. It may take us 10 years, 20 years or something, but I think useful systems can be built that will be answering questions rather than just giving you a list of things for you to read and synthesize your own answer. They're more problem-solving systems rather than just information retrieval systems. The other dramatic thing that happened is the iPhone app, Siri. Again, if anybody has said 10 years ago that you'll be able to ask a question to an open population, I would have said impossible. We don't know how to do that. And there are at least 4 companies that have equivalent technology in speech. Microsoft, IBM, Google, and Nuance, which is being licensed by Apple. And they're all, I think, about the same, equally good. But there are a lot of limitations. For example, one of my 2 complaints to all the recognition systems is they choose not to recognize nonverbal sounds. If somebody shuts the door, or somebody is walking, or some toilet flushing and other things, or disfluencies, where you cough in the middle of your speech. And these things we recognize and semantically understand what they mean, and then we reject it as being unnecessary for the understanding of the speech. But most of the current systems simply do the following. They just say they're all garbage words. They choose not to recognize. They build a garbage model. And that's not, I think, the right. There are lots of shortcuts of that kind that they have taken, both in acoustics. You build an acoustic learning model with multiple Gaussians. I don't think that's the right thing in the long run. So there are lots of interesting issues that have to be solved, but I think they'll all get solved. And the problem, what we are seeing is the systems have become so big, that in order to make progress, we have to get there faster. So anyway, the lessons from these things are unlimited data, unlimited access to computation and memory and bandwidth, and use of statistics that was not anticipated. That all of this, basically almost all these systems use terabytes, multiple terabytes, or hundreds of terabytes of data, and processing all of that takes cloud computing of the kind. The thing that surprised me was Siri essentially doesn't do any computation on board. It digitizes the waveform, doesn't even do the Mel-Kapsel coefficient, and then ships it. And then somewhere, offline, the recognition is done and then sent back. And if you have fast enough computers and lots of them, millions of them, you can handle any number of speakers speaking simultaneously. And so, but all these systems are still fragile. So if you take Siri, what happens when it doesn't understand it? Usually, one of the things in the dialogue systems we did in the 90s that they're using now is what we call case frame parsing. And they do the same thing, except instead of doing travel task, which is all we did, they have 20 case frames for different kinds of tasks. Where is the nearest restaurant? Where is the nearest gas station? The common things people seem to ask. For each one, they have one, and they build all of these simultaneously, and whichever one has the best score gets answered. If they can't answer any of them, or all of them are kind of pretty poor, then they simply apparently send all the data to a search engine like Bing or Google, and whatever comes, they kind of quickly summarize and show a few options so that the user can. So it looks intelligent from the perspective of a user, that it understood what they said and doing the best it can. And so the question then is, what do we want to do? How do we get there? Basically, I already gave you an indication of 4-year-old child machine, and given I only have 3 minutes, I'll try to kind of quickly go through it. Basically, let's agree that all we want to do is to create a machine that has the same level of capabilities that most human beings, if you have some other handicap, you may not be able to do this, have the same cognitive capabilities. What I want you to remember is 5,000 years ago, almost everybody was illiterate, but they were bright enough to see the need to invent writing. They discovered agriculture. They did a lot of things. So it doesn't mean just because you're illiterate, you're stupid, or you don't do problem solving. You solve problems based on whatever knowledge you have at that point in time. So anyway, so I think we know how we can begin to create an architecture for the child machine. I have, in the paper, multiple levels and descriptions of what they might do. But the key thing I want you to remember out of these child machines is that they should be only educated. They cannot, there's no program. There's some architecture you start with. Then you feed it all the sensory data that a child is exposed to, including touch and temperatures and everything. And at the end of 6 months, when the child machine sees the image of the mother, it should smile. At the end of 10 months, it should start speaking pa and ma, right? And there are theories from brain science of how this might happen. And the most important thing there is, unlike conventional systems and conventional programs, these are self-scheduling systems. And in the old days, we used to call it goal-directed architectures. They use a lot of they learn from experience. They use a lot of memory, a lot of knowledge. They tolerate error and ambiguity, and they exhibit goal-directed behavior. And all of them can be built in. And so one of the curious things is, what is a child born with at the age 0? And there are a lot, one of the great things about this particular area is the developmental psychologists have been studying it. They'll give you as much detail as you can swallow about what a child seems to know at the end of the first trimester. Already they claim they know lots of things. And so given that, I think we have a good chance of getting there. So my thesis here, in conclusion, is that we should try to do this. And not only that, it should be done here, started at Microsoft Research, because this is the only place in the world which has enough critical mass of computer science researchers that can undertake such an undertaking. And I'm not saying everybody should drop whatever they're doing and do this. If you take 1,000 PhDs and say 10% of them are going to study this problem, that may be a good thing to do. With that, I'll stop. Thank you very much.
All right. Thank you, Raj. So I realized that I forgot to introduce Raj appropriately. So I'm going to just do that now, since I did take the trouble to do a little research on Raj. So Raj is a university professor of computer science and robotics at Carnegie Mellon University. Obviously, he's a pioneer in the field of artificial intelligence. And among many other accolades, he received the Turing Award in 1994. And now we have Satya. And Satya, let's get you mic'd up here. All right, so Satya is the Carnegie Group Professor of Computer Science at Carnegie Mellon University. Satya is an experimental computer scientist, done a lot of great systems work, particularly known for his work in the areas of mobile and pervasive computing. On a personal note, I still think of AFS, the Andrew file system, as the best distributed file system that I've ever used.
Thank you, Rich.
I wish I could be using it here. All right.
Thank you very much.
Satya.
Is this thing working?
Yeah.
Yeah, okay, great. So thank you for turning 60, Rick, so that we could celebrate. It's such a great thing for you to do. And I want to thank Rich and everyone else who organized this for bringing us together, because I've met people here I haven't seen in 20 plus years, maybe even longer. So what I want to do today is to share my thoughts on a piece of work that I think is the most significant technical contribution that people associate with Rick's career. Yes, of course, after he came to Microsoft Research, done many other things, but the Mach operating system is what is certainly a very major part of his career. So anyone who, is this not working? Ah, it does, finally. Anyone who talked to Rick in the mid-'80s, when he was thinking up Mach, he had been working on, I think Accent was the predecessor, and he was working and thinking about Mach. The excitement he shared, in my mind, when I talked to him, always focused on two central ideas. One, that operating systems had grown bloated and too large. That was true then, it's even more true today. And there was a need to shrink, to simplify, to be minimal. And the second idea, by the mid-'80s, you could run DOS, you could run the Macintosh operating system, you could run Unix, but you had to have a different machine for each. And so Rick said, why should I do this? It should be as easy as moving a mouse from one window to the other to be able to use the right tool for the right job. So the concept of multiple operating systems, or the industry buzzword at that time was multiple personalities on the same hardware at the same time, was another big idea. And so what I want to center this talk on are these two ideas and follow them through the last roughly 30 years. So let's look at simplify and shrink. The first public description of this idea is from this paper of 1986, which I have a cut and paste. Any typos you see are in the original. And it basically is the MicroKernel Manifesto. It makes the point that I made earlier about shrinking and simplifying, and that that's the only way to get it right. When articulated and implemented in the earliest Mach implementations, this became widely recognized as an important idea. In fact, within a few years, I would say within 5 years, everybody who did anything with operating systems believed in microkernels. There was an industry consortium called OSF1, the entire workshops and conferences, the Mach Unix symposia. There were papers in SOSP, the Premier Operating Systems Forum. There were companies which, like Chorus, which used the idea but not the implementation, and there were others like the IBM MicroKernel, which actually did build on the actual code. So this was hot. Unfortunately, by the end of the 90s, things didn't look so good. And in fact, there was a lot of talk and retrospection that microkernels were a dead idea. In fact, here's an example of a typical blog. You can find this. Notice the date, 2006, talking about unraveling the microkernel myth, and then talking about what caused this spectacular failure. Notice, it's not just failure. It's spectacular failure. Okay? This is usual web hype. The good news is that reports of the death of the microkernel vision are grossly exaggerated. A different group of researchers who were inspired by Rick's vision. This is Jochen Liedtke at GMD, and then at IBM Watson, and then Karlsruhe University, and his colleagues and associates, Gernot Heiser, who's now in Australia, and Kevin Elphinston, built a series of microkernels, L3, L4, and their descendants, which have continued to this day to embody exactly the principle of simplicity and small size. And in fact, just a few years ago, the L4 kernel formal verification won the Best Paper Award at SOSP. So certainly in academia, the idea is well and alive. And this is a slide from Gernot Heiser. There are very substantial commercial use of this concept. That in the field of embedded systems, microkernels are doing very well. Okay, so that's the simplify and shrink vision. What about the idea of supporting simultaneously multiple operating systems on the same hardware? Not with a reboot in between, but concurrently. So this is the earliest reference that I could find. It's from 1989, the second Hot Topics in Operating Systems workshop. And it basically expresses the point that is the essence of this idea, which is the kernel becomes a kind of universal socket into which more than one operating system environment can be plugged, insulating it from the hardware itself, greatly simplifying the design and implementation. Great idea. There were real implementations of this idea outside Carnegie Mellon. So this is a cut and paste from a digital equipment paper, white paper. Cheryl Wiesik and her team implemented Mach VMS, which ran concurrently with Unix on the microkernel platform. And the biggest bet of all was placed by IBM, which from 1991 to roughly 1996 had an enormous effort in the IBM workplace operating system. So at one point, believe it or not, there were over 2,000 developers engaged in the task. Now, how over 2,000 people engaged in a task can do anything useful is beyond me. But it's an indication of the amount of investment of resources that they were able to make on this. And it was the case that by the fall of 1992 at Comdex, it was one of these monster events, I don't know if it still takes place, IBM demonstrated DOS and OS2 and Unix, all of these on the IBM microkernel platform. Unfortunately, through a variety of factors, mostly dealing with the engineering challenges of getting the details right, of dotting the I's, crossing the T's, getting the performance right, the problem was far harder than the engineers realized. And in terms of getting out a product that they could sell competitively relative to the other hardware and operating systems, monolithic operating systems, it didn't make it. So the project was canceled, and the last version of the IBM MicroKernel was released in, version 2 was released in 1996. So if you had asked 10 years ago, is this vision of multiple personalities on a common base, is this like an old idea? Is this likely to have any relevance today? The answer would have been, it's history. It was a great idea, they tried it out, it didn't work, forget it. But today, look at any cloud. What you have is exactly the vision that Rick described. Multiple operating systems running on the same hardware with a thin layer of software. Now the name is different. They don't call it a microkernel, they call it a virtual machine. Okay? But the vision is the same. In fact, there has been a raging debate in the operating systems community in the last few years. So Steve Hand, one of the guys who worked on the Zen hypervisor, had this paper in the HotOS proceedings on virtual machine monitors are really microkernels done right. If only these guys back in the 90s had understood this is how you had to do it, we wouldn't have had all this trouble. And there was a rebuttal from Gernot Heiser, the guy who leads the L4 effort, saying, nonsense, microkernels are microkernels, and virtual machines, we don't need them for this purpose. You can go read the original debate. Virtual machines are an amazing concept because they're an older idea than even microkernels. They date back to the 60s when hardware was scarce and people needed to replicate the hardware in order to get access to it. But the emergence of personal computing and personal hardware meant, why do you need virtual machines when you can have physical ones? And if you had asked people in the 1990s, is there a future for virtual machines? I'd say, this stuff is old stuff. Who needs them? And yet, in 2012, the idea is very vibrant, very alive in the basis of cloud computing. And it's worth spending one moment asking why. So this picture shows you essentially how the multiple operating systems on a common base works. And in fact, to be honest, this picture on the left, the narrow-waisted hourglass figure, is true of any interface that separates a producer at the bottom from consumers at the top. In the case of the microkernels, the narrow waistline is the very slender API of the microkernel, the interface of the microkernel. In the case of the virtual machine interface, it's the instruction set. Now, there are two properties that are critical for success here. One is that the waistline be as narrow as possible, because narrow interfaces give you the widest possible range of opportunities on both sides of the interface. It's easy to build a system that matches a narrow interface than one that has to match perfectly across a wide range of interface calls. So that's one. And the other is it has to be stable. If you have an unstable interface, it's very difficult to make it last a long time. So you can create narrow interfaces in software. In fact, that's what microkernels aspire to do. The problem with interfaces is that it's just like waistlines in real life. They have a tendency to expand. And the reason is very simple. If you own the interface, it's extremely difficult to resist the temptation to add just the slight extension to the API that makes your application do superbly, an application that you hadn't thought of. And so bit by bit, this elegant, svelte API becomes one of those bloated interfaces that Rick railed against when he first thought of the microkernel vision. So software is inherently too malleable. And the reason virtual machines have succeeded, I believe, where microkernels had a harder time in this particular application, is because you don't own the interface. The hardware interface is typically built by a vendor, and is even Intel discovered when you change the interface and do something like Itanium rather than x86, the marketplace penalizes you heavily. So for better or worse, stability, even if ultimate narrowness of interface is not there, the stability is there with the virtual machine. So in a little ways, it's useful to look at this from a different angle. Think of an abstraction like process migration. Is Ed Zayas here? So Ed Zayas did a PhD thesis on process migration in Mach. And so he was the second or third person to do a process migration thesis. The earliest one that I know is on the Demos system, way back in the early 80s, 83, I think. But roughly every 5 years, almost like a clockwork, yet another university somewhere in the world produces a PhD thesis on process migration. Okay? And probably one is due about now. Yet, to the best of my knowledge, I'm not aware of any product implementation, whether in an open source system or a closed source system, of process migration. Virtual machine migration, on the other hand, is widely used. It's implemented, it's used in all the cloud computing platforms. It has different names, vMotion, live migration, etc., but the idea is there. So this is an example of where the stability of the interface makes it possible to widely deploy and simplify the administration. So, in a way, the choice to use a hardware interface for this purpose is a little bit like the story of Ulysses, who wanted to listen to the beautiful music of the sirens. But of course, they lured the sailors onto the rocks. So he had the sailors' ears filled with wax, and he had himself tied to the mast so that he could listen to the music, but he couldn't control his sailors to do anything bad. And he listened to the music, and they sailed to safety. So, to wrap up, at the heart of the many, many contributions that Mach made, and there are many, and I've just sort of distilled these down to two simple ideas, was the idea of simplicity and smallness, brevity, which is very powerful, the concept of the microkernel, and the notion that you should not have to do Herculean things like rebooting to switch back and forth between worlds that are best fits for what you're trying to do. That it should be as simple as going from one window to the other. And while the Mach operating system in its original form may not be widely used today, the ideas that were at its heart are very well and alive. Thank you.
All right, thank you, Satya. So next up, Alfred. Thank you. So Alfred, you should come on up now. I think you're up next. I'm sure you're familiar with these. So let me introduce Alfred. Alfred Spector is Vice President of Research and Special Initiatives at Google. Previously, he was an executive at IBM, where he led their software research. Before that, he founded Transarc, a startup spun out of Carnegie Mellon to productize some distributed file system and transaction processing technology. Alfred was also my first advisor at CMU.
Right. My microphone is on, I trust? Mm-hmm. Good. Is Raj back yet? Yeah. Okay, good. Good. Ed left, unfortunately, to go find you. But that was, I'll tell Ed the story later. So I'm going to do three things. First, I want to comment on something Raj said, because I think you'll find it interesting, and it's not too widely known. And two, I want to, of course, comment on Rick, who is, of course, the object of most everything that we will be saying today. Or at least maybe the indirect object, I'm not sure which. Someone in parsing will have to tell me. And then finally, I want to comment a little bit on Satya's discussion, because I was thinking about that in the shower this morning, in fact, without having read it, but I really was. I was able to intuit what he was going to say. So first, Raj, you talked about translation, saying you couldn't anticipate how rapidly statistical machine translation would make progress. But I want you to know you were the catalyst of this, more than you know. Approximately 10 years ago, you may remember that you visited IBM Watson. I was your host, and at the time I was leading the IBM Software and Services research team globally. And you said that translation needed a metric, like word error rate in speech recognition, that would drive the researchers towards near-term concrete goals and where they would continue to try to outdo themselves to improve quality. I think you may know this, I'm not sure everyone else does, but within a year, the IBM Watson team produced the BLEU metric, or the BLEU metric, perhaps in French, and excuse my pronunciation. And that metric actually has been enormously successful, despite what I would say are huge flaws that are inherent in it. But it's still been enormously successful. And I can tell you, within the Google world, that metric has driven the team that did translation to work, incredibly hard, using every possible idea that they could come up with to try to achieve best-of-breed translation across the language pairs that we do. So it was very important, Raj. That was a really good idea. I don't know whether your idea of building a child that is, a computer that does a child will be as influential or not. I would think it would be more so, because it's a broader idea. You need metrics for it. So in any case, so that was one comment. The second one is I do think actually parsing plays a role in translation, though. So I suspect that's true broadly across the world. It is certainly true at Google. So these systems are now beginning to apply what I refer to as the combination hypothesis, that every good idea in AI must be combined to generate systems which are intelligent, and that whether it's Newell or whether it's Feigenbaum or yourself or the statistical people or the machine learning people, all the ideas are going to prove to be good, and they're going to be combined with a multiplicative reduction in error rates to generate systems that are reliable. And we are beginning to show that, I'm sure. I know, because I was involved in the early days of the Watson work at IBM, the IBM Watson system is based on that same concept of using enormous numbers of different mechanisms of extraction to generate increasingly reliable results. So now, that's one comment. So let me now turn to Rick. Rick, so you were at CMU about 2 years before I got there. And I, in a sort of silly way, thought I might be working with someone else when I got to CMU. But since this is being recorded, I shall say no more. And in fact, it turned out that we were going to be working together very heavily. Now, I was very interested in communications when I got there. I had wrote a thesis on high-performance remote procedure call. But you were doing that already. You were already, into messages and, ports and capability architectures for message passing. So actually, you very much influenced my entire career, because I had to move up the stack because of you. But that was actually a good partnership for the most part. Rick, the way I always thought of the world is Rick worked on the operating system level abstractions, and moving into distributed systems, of course, as well. And I tried to work on top of that and build other abstractions, say around transactions or other file systems notions or replication that were built on top. And that was really a very nice partnership. However, despite the fact that it was great, there was one disadvantage in that partnership. Is as computer scientists, when we pitched our work to funding agencies or outside visitors, we did things bottom up. So Rick would get up on stage for 45 minutes and talk about ports and interposing processes with ports and copy on write and message passing. I can give your talk better than you can, probably still. If you have any idea how many times I heard Rick give the accent and then the mock talk, you would have pity on me. So I listened to this over, and then, of course, I would then give a talk on, weighted voting and replication, or how you could make RPC transactional, or this or that, or the other things, eventually, some wide area file systems things. But Rick would leave at the beginning of my talk, because he had a class to teach, or students to advise, and plus he had heard it before. So he didn't need to stay. So actually, you were even more influential, Rick, because I left CMU because of this. It was widely thought that, really widely thought at CMU, that you had to leave when you got tenure. Right? For example, when I got to CMU, Bill Wolfe left, he was tenured, and Anita Jones was tenured, she left. Remember when Bentley left just after he got tenure? There was a whole raft of people that got tenure at CMU that left. And that was perhaps maybe how you positioned your leaving, Rick, I don't actually know. But that's how I positioned it. But it was actually listening to the microkernel talk. Despite its beauty, it's just proof by repetition has limits. So, any case, so that's one story. The second one is actually more serious. The thing that I wrote something for you, you'll see this written down, is your optimism is, I think, such a remarkable and powerful part of your leadership and the benefits you've had on our field and on the organizations that you've led. Rick, as all of you that have worked with him, is just an optimistic, glass 98.7% full kind of person. And I think that's just a tremendous benefit in the field of computer science. Because anything we can conceive of, we actually can do. That's the nice thing about this field, is that we can actually do the things that we can conceive of as long as we're optimistic about it and we execute. That, I think, was Jim Gray's great skill as well. That was dangerous on a sailboat, I regret to say. So it's not such a good thing in sailing. Conservatism is probably better in sailing. But in computer science, it's a great skill. So I think many of you, I don't know if you still do this, but Rick could say bigger, better, faster, cheaper, more rapidly and more fluidly with this wonderful combination of legato and musical quality than anyone else. Can you do it for us now? Please, could you stand up and say bigger, better, faster, cheaper? Please? Okay, would you please make sure he gets high alcohol content beverages tonight so that we can hear Rick do a rendition in E-flat major of bigger, better, faster, cheaper. That being said, Rick also had focus, and Rick definitely stayed focused on a number of things. You can't do everything. He may have had interest in virtually everything, but he did stay focused, and that was another very important lesson to learn. Last story is in 1991, I recall, I don't know if I've ever told you this recently, Rick, but I recall exactly where I was and where I was looking when I got a call from you in about somewhere between 7 and 10 o'clock at night. I was at Transarc in a 20th floor corner office overlooking Three Rivers, and Rick called and said that you had gotten an offer to start a research group at Microsoft, and should you take it? And I remember strongly advising you to do that, because I was having a blast at Transarc, and I was finding myself with an opportunity to really diversify the kinds of interest that I had. It was not that CMU was in any way not great, but I had a much broader set of responsibilities. And I actually thought that you also had that breadth, and that you would love it, and that microkernels were a good thing, but there was more to life than microkernels. So I remember strongly encouraging you. I had, in fact, considered a job offer very seriously about 2.5 years before at this great company. And I had turned it down, so I had experience, and I almost did it. So it was really great to say, you should go do this, and they should pay you a lot, et cetera, and I guess it all worked out well. So I do observe that to some degree, some small degree, perhaps epsilon, you folks at Microsoft that have had Rick as your fearless leader owe that to a degree to the research leader at Google, which is sort of an interesting thing. So last comment I want to just make briefly, because I probably used up too much time, or will soon use up too much time. This comment that Satya brought up, sort of looking back critically at a very important collection of research in the modular construction of operating systems, which is, I would say, the overall framework for this, it's a really interesting thing to look back, in fact, at this and many other aspects of systems and try to draw engineering conclusions about what's right and what's wrong, and and also why things happened as they did. I was reading it turns out I was reading VM papers on the airplane yesterday coming over here over the last few years, from maybe published in the last decade. and was thinking about this on the airplane as well, is why did one thing actually take off more than the other? Why did these things happen? There are lots of other areas where we actually haven't reached broad conclusions as a systems community as to what happened, why, and what the implications are. In my own field, the notion of distributed transactions seemed to be very promising at one point to lots of people. To be frank, we use them much less than we would have predicted. We do use them, there are places, but we don't use them as a fundamental system structuring technique in most places. Why is that? What happened? So I think the kind of analysis Satya just did is a really interesting one. It would be good if those of us in the systems community could ever reach definitive conclusions on all these ideas that we pursued and actually write them down and say, this is actually better for this reason or that reason, or the hardware interface is better for these reasons, or it actually isn't better, it's only because we were undisciplined towards some feature creep or something, and if that's really the reason. But I don't actually know, and I'm not sure it's been studied. So I would so if Raj is asking for a 4-year-old, I'm asking that we analyze all of these probes that we've done as sort of mature adults and actually try to reach enough conclusions that we could tell the next generation actually how to do things. Anyway, Rick, happy birthday, congratulations, keep up the good work.
All right, thank you. Hey, thank you, Alfred. I think we'll hear more after lunch about the funding of Microsoft research. Next up, we have Sandro. That's already turned on. So Alessandro Forin is a principal researcher at Microsoft Research. He's actually been very busy this past week at TechFest. I know his voice is a little hoarse. Those of you at TechFest will understand that. So thanks for joining us, Sandro. Sandro joined MSR in 1994 from Carnegie Mellon, where he was a research scientist working on the Mach project.
Thanks, Rick. I wasn't really sure what this FestSchrift was. I thought maybe it was a kind of a roasting the president kind of thing. So I started with a list, and I realized that maybe that's not what we want to do. But I do want to mention, the first time I met him, it was an embarrassing encounter, for me at least. In those days, we used to actually print code. And there was a printing room in which you go, and there were laser printers already, strangely enough. And you go and pick up your code and look at it and find your bugs and print it again. And so I go and fetch my code and see Rick looking at it. Oh my God. It was one of the 3 gods of operating systems. It was Rick, Cheriton, and what's his name, Sprite guy? Osterhout. And so one of them was looking at my code. Oops. Lucky enough, he didn't dislike it, I guess. Since then, we actually went to work together. It was a while since I saw a color Rick's code, and it was a difficult task he was doing at the time. He was actually working on the IBM PC. He was trying to get X11 to work. And that was a double jeopardy. First, because the VGA interface was, well, you all know what it is. It was worse then. And second, because it was using a compiler that today you all think is a good compiler, GCC. Back then, it was the first time ever that it was used for something that it was in competition to a better compiler. It was, in fact, the only Unix compiler that worked on the PC. And let's just say that he was fighting 2 different problems at the same time. The first work meet, I think, that we had together, I was at the time like Arlequin. There's this serve of 2 masters. I was working for Roberto Bisiani, and we went to Rick's office trying to convince him to get one of those APIs that Satya rightly said that shouldn't be in the operating system, and Rick didn't want in the operating system. And that was the yield API. So if you follow the story, that's something that didn't go away quite as easily as that meet suggested. Needless to say that Rick didn't want that. And so the thing didn't work very well. There was another meeting later on with Eric Cooper at the time. And Eric was the author of the C-Thread library, something they built on this yield idea, meaning have a user mode context switching back and forth easily and write more efficient, share memory-based parallel applications. Eric didn't have a way to handle signals, basically, or exceptions. And I was doing something in parallel. I was trying to build a libc library based on message passing. And that was maybe the idea in which we would bring up a programming environment on top of a pure kernel, which is what we were trying to build with what became Mach 3.0. In the meeting, there was also Avi. And needless to say, Avi didn't like signals at all. So the idea of having anything even remotely related to signals was not in the meeting. So Eric was very pissed out of the meeting. He didn't get to talk anything that he wanted to talk. What we talked instead was this funky idea that both of them came up with. It was, why don't you, when you take an exception, why don't you send a signal, a message somewhere, and use that to build the multiple personalities that Satya talked about. So that really was, to me, that was the meeting where the idea of Mach 3.0 was born. How exactly would you go about having compatibility between multiple environments? And you would be based on low-level mechanisms, traps, system calls, etc. But they would become microkernel, if you want to call it. You didn't call it microkernel. For somebody else who invented the word microkernel. And have multiple programming environment, if you want to call it, coexist. The outcome of that work was a presentation that Rick made at Usenix. And I was in the back of the room when he was showing the system. First he gave the talk, blah, 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 everybody was asleep. And then he made the demo, and people started to wake up. First because Usenix is Unix. And there was a, kind of, well, let's say not acrimony, but competition between Berkeley, say, and Unix and CMU. So they weren't quite convinced at Usenix that we could do what we were talking about, or that it would be anywhere close to functional, or even remotely fast by any definition. So when he brought up Unix and showed a little demo there, everybody was like, "Ooh, it actually works." And there was a guy next to me who says, "Wow, that's impressive, but hey, if they brought up the Mac OS, then I would be impressed." Guess what was the next demo that Rick built up? And that was pretty much, I think, what led to the big success. The audience there, I was in the back, so I saw everybody was jumping up and down and said, "Ooh, ooh, ooh." But we didn't stop there, and so there was also a funny aspect to the Mac days. And Roger Mullen, remember Rob? So he had the idea of getting DOS to work on top of Mac. And I believe that was a very important event for DARPA, because it was the first time they ever paid for games in their budget. I don't know if it was a consequence of that CMU got an audit, and Alfred had to pick up an accent system that had been frozen and power it back up to show that it was alive, and that was the money that DARPA had given us. So on a different aspect, I also got to see Rick can cook. So it was the first time they came over here in Washington. I went to his house, and there was Kira. I remember she was jumping all up and down. Kira's the same age as my daughter, so I had a great time that night, and I missed my daughter very much. But so that was also the first time that I ate mac and cheese. And being Italian, that was a big thing to swallow. As for the quality, let's say I never had mac and cheese ever again. Nonetheless, I hope that shed the light on some aspects of Rick's personality. Rick, happy birthday.
Thanks, Sandro. And we'll hear more from Avi about about Mac OS on top of Mach. Jonathan is an engineer at Oracle currently.
Can't hear you.
Oh, my own mic is off. Sorry about that. So I'd like to introduce Jonathan Chu now. John is an engineer at Oracle currently. Previously, he was with Sun Microsystems. But back in the old days, John worked as a staff programmer at CMU on the Mach project. And so we'll get to hear his thoughts on that.
Thanks, Rich. So my name is Jonathan Chu, and I worked for Rick a long time ago. But I'm going to talk about how I came to work for Mach's fearless leader. So just a little bit about me. I worked on Mach with or for Rick from 1986 to about 1991. And before that, I'd gone to Berkeley. I didn't know what to study until I stumbled across CS as a prerequisite for business, and never imagined that I would, where I would end up working. And so my first job out of college was at PERC Systems, or Three Rivers Computer. And I ended up going to Pittsburgh because my OS professor was John Osterhout. And I really loved my operating systems class. I thought he was one of the best teachers I ever had. And he had gone to CMU. So I asked his advice about going to Pittsburgh. My other job choice was to work for GTE Sprint doing COBOL programming. And I grew up in, near Berkeley. I grew up in Oakland, and so it was a little scary to go to Pittsburgh because the furthest I'd been, outside of California was Nevada. But anyway, my first job was at PERC, and I got to work on the Accent operating system, which was the predecessor to Mach. And then PERC eventually went out of business. But I had a great time there because it was, at Berkeley, we basically had terminals and shared VAXs and PDP-11s with hundreds of other students. And at PERC, I got to use a real workstation with a mouse and Windows and everything like that. And I'd only seen, like screenshots of those things before. So it was a lot of fun. But anyway, eventually PERC went out of business. But a lot of the people at PERC had either, worked or come from CMU. And so they had connections, and basically I got to go work at the CS department. And I started doing speech recognition to start with. And once I got to CMU, I just thought it was the greatest place. I mean, it was so much fun. It was just amazing. Everything from one-legged hopping robots to autonomous land vehicles, everything was just amazing. So I don't know if most of the people know here, but Rocky and Bullwinkle were our unofficial mascots for Mach. And we named some of our machines after the characters from the show. And I was thinking about how would I go about describing Rick? What do I think of when I think of Rick? And it turns out I think of some of the characters from the show. And I decided that I wanted to maybe use that as a way to tell you what I think about Rick and how I feel about him. So I wasn't sure all of you would know what Rocky and Bullwinkle are, because it's a show that aired on network television in the U.S. from the 60s to early 70s. But so I thought I'd better have pictures. That's why I did slides. Anyway, so that's Bullwinkle J Moose and Rocky J Squirrel. And then these are a few other characters, which were basically Boris Badenoff, Natasha Fatal, and the Fearless Leader. And Boris and Natasha were, basically Rocky and Bullwinkle's adversaries. And then the Fearless Leader was their boss. And I was very disappointed when Bob Barron told me, it's like, Rick can't be the Fearless Leader. That's a bad guy. But okay, so I did some research, and Wikipedia at least explained some of this to me, so I could try to figure out does it make sense or not, right? So Fearless Leader was the dictator of Pennsylvania, and basically, and like I told you, he was the boss for the bad guys, right? But coincidentally, we were in Pennsylvania, which to me sound pretty similar to Pennsylvania. And then, but then Rick really was our fearless leader, right? He stuck up for our project and us. And then, I just figured, I don't know how it happened, but he must have been a really good salesman, because basically the CS department and basically our facilities group, even though the name sounds like it might be the janitorial crew or something like that, was actually our group that basically provided the computing environment and the infrastructure for the department. The department and basically the facility group basically, agreed to basically have mock run on ARM systems. And I thought that was great, because, for us, we started out with, BSD, and basically we started changing out subsystems from within it to be, ours. So, the IPC was in there first, and then they worked on the virtual memory system, and Avi did tasks and threads in the summer. And, there's just, but the greatest thing is that, we're switching out all these things out from underneath everybody, and without them having to know, which was really great. And then another thing too is I just figured great, that Rick must be a great spokesperson, because we had so many visitors, and got to work with all these interesting people and companies. I met Bill Gates. I got to meet Steve Jobs. All these different companies came to work with us, and it was a fun time. So anyway, so maybe you guys can help me figure out, which character is he most like. So the next character was Mr. Big, and you can sort of see him there. He's the little guy who's being, there's a flashlight on him, and you can see his shadow. So you can see his silhouette. So you can't really tell whether that's Rick or not. And as far as I know, Rick doesn't wear hats. So Mr. Big is the boss of the Fearless Leader. And Rick was definitely our Mr. Big for Mock. Right? Everybody who worked on Mock worked for Rick. Right? And I listed some of the guys, and I probably missed some people too, because I think Sandra mentioned Rob. But I just want to at least get some of the names down there, because we had a lot of really good people to work with who were really smart and really nice. But you could argue that the head of the CS department, or Howard Wackler, who was our vice provost of research computing, maybe they were Mr. Big, right? So anyway, you couldn't tell from that little picture before what Mr. Big looks like, so I, Googled for images of Mr. Big, and this is what I got. But anyway, Rick looks more like this Mr. Big than Howard does, or the head of the department did at the time. Then the last character that sort of reminds me of Rick is Mr. Peabody, and this is a picture of Mr. Peabody and his boy Sherman, who was this young, enthusiastic, naive boy who basically followed Mr. Peabody going through their Wayback Machine for time travel. And so anyway, Mr. Peabody, so Rick is a genius, and he wears glasses. And he definitely had students who were bright and young and naive and enthusiastic like Sherman. And he even had staff people who were like that, because I was a staff person working for him. And then, but anyway, so the interesting thing is he didn't have a time machine, but we had this thing with Rick that we called Rashid time. And from what I remember, I believe where it came from is a bunch of us were in Rick's office one day, and we were talking about some technical task that had to be done, right? And so Rick gave us an estimate, it's easy, guys. It's sort of like, what Alfred said is, Rick is very optimistic, but the other thing too is he's very fast. I mean, he talks fast, he walks fast, everything goes fast, right? I mean, he could be very patient and slow down and talk to you, but mostly, he moved quickly. And so anyway, his estimate for this, how long this thing would take was, I forget, 1 week or something. And I think Mike Young at the time said, oh, but that's Rashid time. It's like to translate that to, normal time for human beings is you basically, double it and then go up to the next unit of time. So 1 week in Rick's, might be something that Rick could do, but for us normal humans, that would be, 2 months or something, right? So anyway, that's, at least where I could see there's some time distortion, almost like a time machine. Just to conclude, so Mr. Big and Fearless Leader were bad guys, and Rick is a good guy, right? So I'm not sure about them, but I know at least in name he's like that, and he definitely was our Mr. Big and our Fearless Leader. And then maybe he was most like Mr. Peabody. But anyway, the bottom line is I consider Rick to be a great leader, a teacher, and a friend to me. I mean, he's very nice, he's very smart, he was productive, effective, fast, all those things, and always very calm and patient with us. So anyway, I always think of Rashid time whenever I think that something is hard or will take a long time, just to balance my perspective to be maybe a little more realistic. Anyway, thank you. And belated birthday, Rick.
All right, thanks, John. That was great. Listening to you talk about Rashid time reminds me of another related factor, which is the Rashid reality distortion field, which I'm sure some of you have heard of before. And so that was a related concept that would, play out in Rick's office. Things would appear different somehow in Rick's office or work better in Rick's office. So now we've got Bill Belosky. So Bill very recently moved to a new job at Microsoft. He's now technical assistant to the president of Microsoft's server and tools business. But Bill previously was a principal researcher in MSR, having started in 1992, so one of the old timers. Bill was a staff programmer on the Mach project as an undergrad at CMU, and after which he went on to the University of Rochester for his PhD, which is where Rick, of course, did his PhD. So you have your mic on, Bill? Just grab either one of these.
Okay.
And you're using PC4. So that should be getting. There it goes. All right, Bill.
Now you have to turn on the power switch. Yes, well, I don't know for hardware. So I'm going to talk about the Tiger project, which is something that happened a good bit later in Rick's career than everything we've been hearing from CMU. But before I do that, I'm going to add some personal reminiscences. So Rick has had more to do with my career and getting me to where I am than anybody, with the possible exception of my father. I was an undergrad at CMU, and round about December of 1985, I went in to figure out what my schedule should be for my last semester as an undergrad. And I thought, okay, it's my last semester, I should make sure that I actually get all the set of classes that it takes to graduate. So I went in and talked to my academic advisor, and we determined that was the empty set. And so I was left with a choice of taking a bunch of electives or trying to find a job. And so I went and knocked on Rick's door and told him this story. And he was sufficiently intrigued that he thought, well, I'll take a chance on this guy and hire him, because who comes up with a story like that? Usually you find out that you don't have enough credits to graduate when you think you did, instead of graduating by accident. So he hired me. And he started me working on Mach. We didn't have a real formal interview process there, and so he neglected to ask me questions like, do you know C? Answer, no. Have you ever written kernel mode code for anything? No. So I started off, I bought a copy of Kernighan and Ritchie, and learned how to program in C, and started working on Mach. And so he gave me the IBM RT PC and said, port Mach to run on this. It's a portable operating system. It shouldn't be hard. So probably most of you aren't familiar with the RT, but so at the time Mach ran on the VAX. There is almost no 32-bit machine that's more unlike the VAX than an RT. The VAX is little endian. The RT is big endian. The VAX has what everybody would think of as a normal page table. The RT had this bizarre inverted page table thing that was a weird hash table that had the beautiful property that if you got it wrong, the machine didn't tell you what happened. It just displayed 88 in the little numeric thing, and then you had to pull the power plug out to get it to start again. So it was exciting. But I went ahead and ported Mach to the machine, and I had a bug that was due to the virtual memory system working differently, and the bug took a while to find, and Mach didn't work right on the machines while this bug was going on. Eventually, I found the bug, and Rick came into my office and asked me what the bug was and whether I had found it or somebody else. And I told him, well, I explained the bug and told him that I had found it. And then the switch clicked, and he decided that I was okay. And that's probably the most important bug I've ever found in my life. So time goes on. I go off to grad school at Rochester, which is not entirely coincidental that that's where Rick went. And I'm getting towards the end of doing my PhD, and I'm on a plane. I go on a trip to do some random thing, and I happen to be on a plane from Pittsburgh to Seattle in the summer of 1991. And sitting in first class is Rick. Now, it didn't occur to me that Rick would never pay for a first-class ticket on his own, that something must be up. I just thought, okay, he's going to UW to give a talk or something. So this is a picture of the two of us from CTAC from July or August of 1991. Of course, what Rick was doing was coming out here to interview for a job, but I didn't know that. Mostly you'll note that both of us had much better hair then than we do now, although mine was a little messier. So shortly after that, I decided to, there was time to graduate and I should go and find a job. So I printed up my CV and mailed it out to a bunch of places, including mailing it to Rick at MSR. And I didn't really hear anything back. And then I get some email from Rick that says, well, would you like to come and work at this new research lab, which then was 15 or 20 people. And I said, well, yeah, that's why I sent you my CV. And he said, well, I never saw that. It got picked off before it got to me. Here's a fax number. Fax your CV to that. So I did that. And I came out and I interviewed. And then I went back home to Rochester. When I got home, I found an envelope waiting for me from Microsoft that said, we see no interest match with you. Thanks for applying. So once again, it's only because of Rick that I got this job. And by the way, the thing was dated before the time of my interview. It was clearly a response to the mailed in, so someone found it. Anyway, on to the actual topic that I wanted to talk about. This is a joke that several of you will think is very funny and nobody else will get, but Rick will probably appreciate it. So in early 1993, we were all at lunch, and Rick, me and Bob Fitzgerald and Joe and everybody, and Rick says to us, what would it take to build a video server out of PCs? And we didn't really know, so we started thinking about the problem. And you have to understand the context of the time. The machines we were working with were 60 megahertz, 486s or the first Pentiums that came out. They had a few megabytes of memory, and we thought that a 10 megabit a second Ethernet was a pretty good network. And I remember getting 2 gigabyte disk drives and being in heaven. Okay, so these were very uncapable machines. And so the question was, how can you take video, and to get decent TV quality video requires a certain amount of bandwidth regardless of how good your machine is, because people's visual systems are what they are, and it requires a couple megabits a second at least to do that. And so we sat around and thought about the problem, and by we I mean mostly Bob Fitzgerald, and he came up with a solution. So the issue that you get is you could take a computer and it could source some number of video streams, but the curve of popularity of videos, if you look at movies, it's this sort of Zipfian curve that just has a lot of weight in the front, but then a very long tail. And so the problem with this is if you would take a movie and you put it on a machine, you'd have one popular movie, and you'd run out of bandwidth on that machine, and all the rest of the machines would sit idle because you need a certain amount of capacity. And remember, 2 gigabyte disk drives doesn't store a whole lot of movies. So the brilliant idea that Fitz had was, well, let's take the movies, cut them up into small chunks, say a second, and stripe them across a whole set of machines. So now you can, I just knew that was going to happen. No, I do not want to reboot. No, you know, I gave a talk at CMU one time and PowerPoint crashed in the middle of my talk. It's the only time I've ever seen it crash. It just, so we got the brilliant idea, Fitz got the brilliant idea of striping across a bunch of machines so that you can divorce the bandwidth that you get on the machine from the storage. And I'm not going to go into the technical details, but it worked really well. And we were able to take these very bleeding edge, very low capacity things and network components we bought from 4 systems that really barely worked, honestly, but they did work, and build a video server that did things like playing this Natalie Merchant video that you see. This was the one piece of test content that we had. It's 10,000 Maniacs, and we listened to this thing over and over and over again. Anyway. So we built this video server, and we started doing demos, and we showed it to people. And one of the demos that I remember was when Bill Gates came in to see it, and it looked, it was nice, sort of high quality full screen video, which we got on the clients by having a piece of hardware that did the MPEG decode because the machines were too slow to do that. And the thing I really remember is that Bill looked at that and said, "Wow, I had no idea that computers could do video that looked like that." So this gives you some concept of how far out in front we were. Okay, Bill Gates had never, this is the first time Bill Gates ever saw full screen video was in our lab. So we put this thing together, and we did a road show for it. We did a big rollout thing in downtown Seattle, and we had a lot of press that came from that. And you can see glasses were also different then than they are now. But we were able to put this up and display dozens and dozens of TVs running off of these really cheap PCs, and we got a lot more. Actually, more press came out of this, I think, than any project that I've worked on. It was really fun, and I got to play with the flying PowerPoint stuff to show you all the press that we had. But the end of the, I'm running out of time, so I'm gonna wrap this up. But what we, as I told you, it goes on and on. What we got out of this project was the ability to serve high-quality video to people in 1996 or 1997. And Microsoft turned this into a product. No one bought the product. We released the version, blew up the group, and decided that video and computers was not going to work. And the reason that this happened actually is because the network, there was not enough network bandwidth to get the video out to where it was going. We had solved the server problem. And if you think about it, giving up on video in 1998, which was when we did that, was just a horrible decision. If you think about what Netflix, the streaming half of Netflix does, or YouTube, we could have owned those businesses if we had stuck with this. If we'd been willing to ride out waiting for the network to get better, because we knew it was going to get better. We didn't know how, but we knew it was going to happen. And MSR put us way ahead, largely because of Rick. And it's a shame that we didn't stick with it. But at least we can feel good about ourselves for having been there first. Anyway, Rick, thank you very much. Thanks again for my career. I really, literally would not be here without you.
All right, thanks, Bill. So now we're going to take a short break, and we'll resume in about 20 minutes at 10 minutes to 11. So we'll start back at 10 minutes to 11. Thanks.